last speaker of the day is Volker Bromm, black holes and supernovae in the early universe.
All right, at the very end of our first day, back to the very beginning. When we consider the cosmic timeline, then the first billion years is the crucial time where the universe went from simple beginnings to all the complexity that followed afterwards. And of course, many people in this audience, they have worked on working out aspects of this transition. But when we think about this, then the first stars, the first galaxies drive this transition. But then also, in particular, this brings us to the role played by the first supernova explosions and the first accreting supermassive black holes. And when I was thinking back about my time at the CFA, then these two papers, they stand out in my mind. The formation of the first supermassive black holes with Avi, and then with Lars and Naoki Yoshida, the formation of the first supernova explosions. And by coincidence, they appeared in the same volume of the APJ. So that really, at some point, for me, was the highlight of my time here. Just to briefly mention this, the model that Avi and I worked out, how can the early universe really managed to build supermassive black holes rapidly in one place. Later papers have added additional physical detail to this model, and then also the Biegelman et al. Paper introduced the name direct collapsed black holes, DCBHs. So this is now how this model is known, but basically what Avi and I put into this paper, the idea was all there. And then, when Lars, Naoki, and I thought about the first supernovae, then back then really we were thinking about pair instability supernovae. This was driven by the picture at that time that the first stars really had masses that get us into this regime. And there is a history, right? Going back to the 60s, this idea was introduced. And then in the early 2000s, it was revitalized, driven by the predictions for the mass of the first stars. But let me also say that when I was thinking really about these papers and reflecting on my time at the CFA, then I absolutely mirror what I think we all feel. Tremendous gratitude. Thinking back, this has been a magic time. And really then Lars, Avi, Ramesh, of course you were there back then, 20 years ago, and you have created a very, very special magic place. And we really owe you, as was said before, a huge amount of gratitude. Just a wonderful place you have created. So much inspiration, so much magic, as I said. So going back to the science, we have this standard model to understand the early universe. And of course, this was mentioned before. Right? We understand the cosmology, we understand the perturbations, and for the first stars galaxies, we also have a very good understanding of the baryonic ingredients, right? Cooling, chemistry of the first stars. And then if you put this together, then we get the prediction of, that the first stars have this initial mass function that was top-heavy. As Anastasia mentioned, summarizing some of the IMF predictions in the literature, there's no convergence, but there is agreement on the top-heavy nature of the first stars. And in this case, this is expressed in a log-flat or nearly log-flat mass distribution. But again, there, of course, the details, there's no convergence. But we all agree the first stars had this top-heavy IMF. And then from that, we get to the question of how do these massive first stars die? Then this summary plot was famous at the time, still is very useful by Hager and his collaborators. How do massive stars die? So population free, zero metallicity, initial mass. Then there are these islands, 140 to 260 solar masses. This is the island of pair instability supernova, which was of particular interest to Lars, Naoki, and me. But then, of course, also progenitors of a few tens of solar masses. We have core collapse supernovae, and then in between we have collapse into black holes. So all of this plays a role, black holes and the first supernovae. Although back then, right, we thought pretty much all of the first stars die as pair instability supernova. Now the picture is that the bulk of the first stars probably die as some variant of a core collapse supernova, and then there is a smaller group of pair instability supernovae. But now if we just start with some remarks on black holes in the early universe, then schematically, right, we have this, we could call it the great timing challenge. So black hole mass, function of time after the Big Bang, then, well, we have observations. And of course, this was before the JWST. So back then we had the SDSS, really supermassive quasars up to redshifts of 6 or 7. Then the question is, right, how can the universe build them in the brief time available? So if we start with a stellar remnant, even a POP3 remnant, which might start life at 100 solar masses, then, well, it turns out that feedback effects typically limit the growth of these first stars. And then at some point, really, we run out of time and it's difficult to explain how we get to this target line. So then that brings in other players, stellar dynamical collisional pathways, but in particular, the direct collapse black hole. So we start with something that is already massive, has a head start, and then, right, with episodic accretion close to Eddington, right, we can explain this. That is the basic picture. And then, of course, with JWST, now the problem has gotten much more serious, if you like. Right? This is just right, the version that came out from Sears. The very, very broadened H-beta line implicating a 10 million solar mass black hole. But there are now many, many more examples. So now basically with the JWST, we know that we have the verdict. The universe created supermassive objects already within the first 500 million years. And then if we start again at the same plot, black hole mass versus redshift, this is sort of the sources that we knew before. Now we have sources that push this challenge, the timing challenge, to much earlier time. And again, then, this implicates this idea that we may have to invoke, at least for some of those cases, direct collapse black hole seeds. So the problem now is much more serious. And as I said, if one just invokes vanilla pathways, stellar seeds, and sub-Eddington growth, so then you would have a situation here. This was a simulation, that my student Junyoung John did. So this is the accretion rate as a function of redshift again. Red is Eddington, what we need to have efficient growth, but then we end up with something which is way sub-Eddington. So this pathway really is challenged. So then, the idea of heavy seeds the idea of direct collapse black holes. So in very, very brief terms, and this is sort of a simulation that Fernando Becerra did when he was a graduate student here at the CFA. So we have the cosmic web, and then we identify special target halos, and under certain circumstances, we can then have this direct collapse black hole mechanism operate. And it operates when the following conditions are fulfilled. So if we consider the temperature as a function of density, when gas collapses in the dark matter host halo, then of course at first we have adiabatic heating, and then eventually we have cooling. And the cooling is due to molecular hydrogen or metal cooling. And then this cooling drives star formation. So at some point, if we want to condense gas, have it fall into a halo, star formation is inevitable. But then in the early universe, there's sort of this special possibility that only works in the early universe, because if we push it into the early universe, we can take out the metal cooling, and then if we invoke strong Lyman-Werner flux, and that was sort of the idea that Avi and I worked out, then it's possible to also dissociate the molecular hydrogen. And then what one can have is the situation that adiabatically we heat it to 10,000 Kelvin, and then we have an atomic cooling halo that allows collapse without fragmentation. So this is sort of this magic solution, We have collapsing near isothermal a gas that does not fragment, and then basically it reaches high densities and brings in enough mass to seed a supermassive black hole. And then what Fernando Becerra worked out is, then of course in detail, when one looks at the build-up, then one finds that it's possible to have very, very high accretion rates. And they can be maintained without feedback for 10,000 up to 100,000 years, and then the mass that can be reached is something like 100,000 solar masses. This is sort of still a matter of where exactly is it terminated, but this is sort of the ballpark that one gets. And then again, just to say this. Then just one example, there are now many, many papers. It's a deluge of exploding papers, and I apologize to anyone in the audience who works on this and whose paper I do not explicitly mention. This is just a cartoon, broad brush run through. This really would warrant a full-blown review paper, really. There's so much activity. But just to say this, then if one starts with a DCBH seed, invokes something like close to Eddington, then one gets these sort of pathways that we worked out in a simulation, these solid lines, then one can hit the sources, the masses that are observed by the JWST, the CS source, the famous UHZ1 source, which really is a strongly implicated DCBH candidate. So all of this really is putting very much emphasis on the need for these heavy seeds. But then just before we move on, also to just say this, of course, there's another opportunity and way that the early universe could put in black holes early, and this is primordial black holes. Obviously, if the black holes are there from the beginning of the universe, from the inflationary fireball, then of course, then the whole game is different. How can we build the first supermassive black holes? Well, I mean, as was said before, of course, 20 years ago, but probably still 10 years ago, we all believed that we know what the dark matter will turn out to be, supersymmetric WIMPs. And of course, I think as was said before, Avi made the point at lunch, the WIMP is not showing up in the laboratory. So I think as astrophysicists, we have no choice. We have to broaden our horizons. And this was already said by various speakers also, Mark Vogelsberger said this, we have to now broadly explore. And PBH, primordial black holes, is another opportunity. And of course, when one thinks about these objects, sort of the mass, and then the fraction of the dark matter that is in PBHs, there are constraints, and the constraints are sometimes really, really quite strong. And just to also say this, sociologically, sort of when I started to think about primordial black holes as a possibility, then I learned that sociologically we are sort of having two parallel universes. There are people who work on PBH scenarios. They come from a particle physics background, and they typically they are all in. For them, this is the only game in town, and they try to argue that 100% of the dark matter has to be in PBH. When people from our community, astrophysically trained, people think about PBHs, then sort of we are more careful, and then we typically say, well, maybe sort of a fraction, 1%, 0.1%, So there's this interesting sociological divide, but I think it's really an interesting scenario to explore. And just to show you one example, and this was a simulation led by my former student. He is now a postdoc in Cambridge, working with Anastasia Fialkov, Boyo and Leo. So what we did is we compared first star formation in standard lambda CDM, and then compared with, in this case, 0.1% of the dark matter is in sort of 30 solar mass PBHs. And then what we found is that, first of all, most of the evolution of the universe stays the same. And in particular, there's the same kind of thermodynamics, cooling because of molecular hydrogen, the same kind of mass prediction for the first stars. All of that stays in place. But what PBH generically gives you, also for these relatively modest masses, it is accelerating structure formation. So then everything happens earlier and happens in more massive structures. And again, sort of 30 solar masses is modest. And then at some point, we really got audacious, Bojan and I, and then we also explored what can we do about this crisis in cosmology that was mentioned before, this famous Boylan-Kolchin plot, stellar cumulative mass density as a function of stellar mass, right? These curves are predicted by lambda CDM, 10% star formation efficiency, 100% star formation efficiency. And Erika Nelson, right, also mentioned, of course, then we had for a while these predictions. I think these are the official Labbe et al. Early results where you really, right, you are in this completely impossible zone. Of course, now, as we have discussed and we know now there are astrophysical ways to push these points back below the 100% line, but 100% is still pretty extreme, right? It turns out it's not easy to accelerate structure formation beyond lambda CDM. It's easy to delay, right? We have been very creative in delaying structure formation, but if you think about accelerating it, right, this is really tough. You can play with a timeline, early dark energy, but otherwise, right, PBH is sort of the only way to really accelerate this. And then indeed one can populate areas even beyond the lambda CDM one. The price we had to pay here, we had to assume something really pretty crazy, right? Billion solar mass primordial black holes, primordial black holes may well exist, but I doubt that billion solar mass black holes exist. But again, still the message is, right, what PBH really gives you, this is interesting, is it gives you a chance to accelerate structure formation. So this is something that I think is worth exploring more. And then very briefly, before we go on to supernova in the early universe, one more remark regarding population-free black hole remnants, right? Of course, we have this growing phenomenology from LIGO Virgo. There are some cases, and in particular, this is sort of a very famous case, GW 190521, right? This has two black holes merging that are really difficult to understand. Their existence is difficult to understand in standard classical stellar evolution theory because they lie in the pair positional pair production mass gap. And there also then there may be a role for population-free stars, because with population-free stars, right, sort of, this is sort of this magic zone that you have to populate to explain the source in terms of remnant mass. And so standard scenarios don't easily get you there, but with POP3, it's a way to populate this area. And to first order, the reason is the first stars, they are much more compact than present-day stars, so they can survive these instabilities more easily. Okay, so shifting gear, the role of the first supernova in the early universe. Again, there's sort of this idea, core collapse supernovae versus pair instability supernovae. And again, right, Anastasia showed the range of predicted population-free IMFs, and this sort of is a parameterized treatment that Alex Lazar and I did a couple of years back. And then, right, now sort of the idea is that the bulk of the first stars dies in the core collapse regime with a much smaller fraction in the pair instability. So we have to basically have a scenario if we want to understand the impact of the first supernovae in the early universe, right? We have to have this branching ratio in mind. And when one simulates this, then the feedback from these two cases is dramatically different. So the pair instability case is much more dramatic. It puts in bubbles of huge entropy into the early intergalactic medium. It's very disruptive. And the universe takes about a local Hubble time to recover and recollapse and form stars again. But what you also have is what pair instability give you, they give you a huge amount of metallicity. So they put in a metallicity floor locally at the level of about 1% solar. So there's this double nature. But then on the other hand, when one goes to core collapse supernovae, they have a very different kind of feedback. So again, sort of this is temperature, this is sort of the visual radius of the host halo. In this case, right, it's a mini halo. And well, then what one finds is that part of the material escapes to the IGM, but there's very rapid fallback and prompt recovery. And also, right, the metals, sort of roughly 50% make it out into the IgM, 50% stay. So then after, right, less than about 10 million years after the explosion, the system already recovers and can form stars again. So it's a much more rapid way of feedback. But then, right, in cosmological terms, if we consider, right, how the early universe is really enriched, and what one finds is here, just looking at the total metallicity from all stars at the time, population 2 and 3, right? White means primordial, pure hydrogen helium, and then we have these islands of enrichment. But then the message is that wherever, right, the universe tries to form galaxy stars, the high density regions, there are metals in place. So although large volumes of the IgM remain pristine, there are metals everywhere where galaxies form. So basically, metal-free star formation is quickly hidden by population 2 star formation. And the prediction this prediction was made before the JWST was launched, right, that the JWST, even in their deep fields, will find metal-enriched system at the level of at least 1%. And although, of course, quite a few of our theoretical expectations did not come true, and JWST absolutely shocked and surprised us. This prediction, right, if you work within some variants of bottom-up structure formation, you have this universal metallicity floors in the galaxies that the JWST can see. That came true. Then also, right, one other thing is, if one looks at the formation of a first galaxy, sort of, this is a billion solar mass galaxy, and just look at this plot, right? This shows the metallicity. In this case, black is primordial, pure hydrogen helium, and then, right, the colors might show metal enrichment. Again, right, sort of, there's sort of 1%. There are metals everywhere in the first galaxies, and then when one zooms in, right, the other message is this is really the first time that the universe can form a galaxy after the very first star had formed, and it's already a mess. It's already a real complexity. So the universe puts in complexity from the very, very beginning. And of course, if we then really want to go to this simplicity of the first stars, this is even beyond what the JWST can see. And then just to finish up with this. As I said, Avi and I, we started to, Lars and I, we started to work on this early on, but then with Tim and Hartwig, Avi and I returned to this question, and we asked, okay, right, at this point, there's this theoretical expectation that pair instability supernovae could be created in the early universe, but at this point, there's no observed confirmation of a pism. We expect them to be there. We also expect them to be rare, but why haven't they been found? There's sort of one indirect detection, because, right, one other way to detect these first pism is that they create metals, they die, and then they leave their abundance pattern to the second generation of stars. This is sort of the subject of stellar archaeology. Again, right, there was a very, very substantive search for decades for extremely metal-poor stars that carry the signature of these pair instability supernovae, and none was ever found until quite recently. There was, I think, last year there was a paper in, I believe, Science that came out of the Lamos survey, where there was a case predicted that really seems to show the abundance pattern of a pism. But of course, we also want to see the pism explosion in the when it is active and alive, so to speak. So in this paper, right, we basically looked at light curves, and again, right, there's lots of detail. Depends on the progenitor mass, but the message is in terms of luminosity. In terms of brightness, right? These sources should be bright enough so that the JWST should be able to pick them up. But the challenge really is that they are extremely rare. So a typical survey that the JWST has carried out so far will just miss them. So there's this true problem of a needle in a haystack. But again, of course, right, this is one of the super exciting things where we need to invoke serendipity, and we might get lucky. Right? The prediction is yes, the early universe could put into place DCBHs, but also the early universe should have been able to put into place pair instability supernovae. So these really extreme but also super interesting astrophysical objects. And just to conclude, I bet you by a microsecond time. So this is scary. This keeps you going. Okay, right. So as I said, right, understanding the first billion years, right, this was the focus of my time here when I was a postdoc, has been the focus of my work ever since. Of course, also really is clear, right, the ITC is one of the world centers to work out, right, the first billion-year frontier, having put into place the vital science case. I think Erica had said she blames us theorists for the JWST, and I think right there's of course some truth to this. And I guess right at some point there are some missions that die, I believe, right, because the science case is not strong enough. But of course, right, with the NGST, the JWST, right, the science case was so strong, right, that I guess we got the U.S. government. I always tell my donors in Texas, right, it has the cost of an aircraft carrier, and of course that impresses people. But I think with that, I thank you again for your attention, and thank you to everyone here at the ITC.
Oh, yeah, go ahead.
So Volker, DCBH.
Yes.
One issue that I don't hear discussed very often is angular momentum, right? How do you take this very fluffy piece of gas and bring it down all the way to the event horizon of a black hole?
Yes.
It must involve magnetic fields. It must involve MHD processes. How well has this been studied?
Yes, so this is exactly what Lars and I challenged Fernando Becerra with, right? And there is a substantial section in his paper on exactly this. So there are we believe there are hydrodynamical shock-based transport mechanisms. There are gravitational torques. We don't have MHD in the simulations, but when we analyzed the simulations, it's a very turbulent situation. So we believe that we can account for the angular momentum transport.
Is there a simulation that actually takes a big cloud of gas and makes a
Yes. It was a repo, starts with cosmological initial conditions, and then it's a zoom in. The zoom in is pretty big. So yes, I mean it starts from initial conditions, and it traces. Of course, right. We cannot resolve anything like the Schwarzschild radius, but I mean, right, it takes it to densities that are high enough that we believe the point of no return has been reached.
Actually, it goes through a supermassive star, and Stu Shapiro considered spinning supermassive stars and concluded that it's not an issue.
Yes, that is true. I was the idea is you have a primordial cloud, then there is a short-lived about 100,000 years short-lived SMS phase, supermassive star phase, and then as Avi said, then it's a gravitational, a GR post-Newtonian instability. So that I swept under the rug. So our prediction actually was, in this regard, I guess it's a misnomer. We had a supermassive star, but we argued the supermassive star is unstable. And indeed, I think at that point, just by coincidence, Stu Shapiro's paper had appeared, so we could cite that right as a final step. So we don't really make a black hole; we make a supermassive star or a proto-supermassive star.
On this topic. So we're doing simulations, turbulent boxes with external radiation and also following the radiation of the star with primordial chemistry. And I wanted to know what your opinion, we form these supermassive sinks, stars, which will eventually become this direct collapse scenario. But what we find is important there is fragmentation, right? Preventing the gas from fragmenting into smaller and smaller clumps. And so, once you add in an external radiation field and maybe you start to seed with some metals, in your view, how does that change that fragmentation picture? Because you also start to change the cooling.
That's exactly the key. almost everything that you want to do is like you will get gas collapsing into fragments. That is indeed the challenge. So then, admittedly, with some degree of fine-tuning, you have to have the right conditions to prevent any cooling. Of course, the metals you just postulate, you make the gas metal free, and then you have to take care of
but even with the H2 cooling, we find that we still get fragments. So you have to prevent the H2 formation.
Absolutely. So Lyman-Werner radiation.
Yeah.
So it's the Solomon process, right? And of course you have to really blast the cloud with a pretty strong influx of Lyman-Werner photons.
Yeah.
So that is indeed the challenge. And of course, then the question is how much fine tuning is needed. Is needed, but how rare are these objects? Because if we argue that JWST finds supermassive black holes pretty much everywhere, then of course this scenario is challenged.
Right. And where are the Lyman-Werner photons coming from?
Again, another thing that I swept under the rug. So, one scenario is a double collapse. So basically, you have synchronized halos in a biased region. One dark matter host halo by chance collapses a little bit earlier, triggers normal star formation. And there's a starburst. The starburst triggers the laggard that lags behind a bit, and then, but it's also close by, so that you can argue that there is a strong flux. So there's some fine tuning. I mean, when Avi and I first, we were not worried about this because we wanted to explain quasar seeds, right? And then we had 1 in a gigaparsec. So maybe being rare and difficult was good. Of course, now in the rare, of course, it's different. Now, of course, it has to be pretty efficient. So my guess is that what we have in the early universe, probably, right, there is a spectrum of possibilities. So, I mean, there are also papers that work out, you start with a stellar seed and then you have episodic super Eddington accretion. Right? And so probably we need these different pathways.
We have another question? Otherwise, right there, okay.
Hi, yeah, very, very nice talk. I'll ask a final little bit philosophical question just to wrap this up. So you were mentioning the argument that we all use about the Eddington limited accretion from growth from the seed. So regarding the two black holes that you mentioned, the UHC1 and the Larson, do you think that we are already at the point where super Eddington accretion cannot explain this, even starting from a light seed? Because to grow those two sources, you need a super Eddington of maybe 1.5 to 2. So it's not 100. Is this already enough, or we need more to prove, like definitely that heavy seeds exist?
My take is with what we know so far, what JWST has told us so far, we cannot exclude one of these pathways. I mean, of course, having a heavy seed obviously gives you a head start, but I mean, at this point, I think you can still argue that you might have sufficiently strong super Eddington. But I mean, super Eddington is super Eddington is achievable if you have really consider extremely high densities, extremely small scales, and you can sustain it for short amount of time. But then in the end, I'm not convinced that we can sustain super Eddington for sufficiently long, because at some point we also have to replenish the inner accretion disk. And also, super Eddington, of course, but then it forces the system to breathe. There's a super Eddington spike, and then the system reacts, radiation pressure, and then having a very sufficiently long duty cycle of super Eddington is difficult to achieve because there's this breathing mode. But I mean, this is I think. This is an open question, but of course, obviously, if JWST pushes, right, to a little bit higher redshift, of course, at some point, then of course, we will get so constrained that we can start to exclude. That's just my take. So at this point, but I mean, I think probably, I guess, Avi asked about timelines, so my guess is 5 years.
Wait, with that, let's thank Volker again.